A boat is being rowed in a river. When the river is still or there is no current in the river, then the velocity with which the boat moves is the velocity of the boat with respect to the ground, or the velocity of the boat with respect to a still river. And this velocity we denote by VB with respect to R, so the velocity of the boat with respect to the river. In this situation, the river has no velocity as there is no current. Now let's look at a case where there is a river current. Here, the boat is being rowed to the right, and there is a river current also acting to the right, that is, in the same direction as the boat. And as you can see, the boat moves faster than earlier, since the river current is aiding the movement of the boat towards the right. So it is also contributing towards the movement of the boat, and as a result, the boat moves faster. We represent the velocities using vectors. The red arrow, VB with respect to R, is the velocity of the boat with respect to the river. So this represents the velocity of the boat with respect to a still river. The blue vector VR is the velocity of the river, which is assumed as the velocity of the river with respect to the ground. So if there was a leaf floating on the river, then the leaf would move with a velocity of VR meters per second to the right. If there was no current, the leaf would not move, otherwise it would move at the same rate as the current. Both these vectors point in the same direction, so now using these, let's obtain the velocity of the boat. By definition, the relative velocity of the boat with respect to the river is the velocity of the boat with respect to the ground minus the velocity of the river with respect to the ground. And rearranging, we get the velocity of the boat with respect to the ground as the velocity of the boat with respect to the river plus the velocity of the river with respect to the ground. So if we do a vector addition of VB with respect to R and VR, we obtain VB, the velocity of the boat with respect to the ground. And you can see that the boat moves faster as seen from the ground, although the boatman puts in the same amount of effort. So to an observer standing on the riverbank, the boat will definitely seem to move faster when there is a river current in the same direction as that of the boat. But what would happen if the current is in the opposite direction? This time, the boat is being rowed to the right, and there is a river current in the opposite direction, that is, to the left. This will slow down the boat, since the river current is now not aiding but hindering the movement of the boat towards the right. In vector terms, VB with respect to R is to the right, since that is the direction in which the boat is being rowed, whereas VR, the velocity of the river, is to the left. In order to obtain the velocity of the boat with respect to the ground, we have to find the resultant of these two vectors. We add the two vectors pointing in opposite directions, and we obtain a smaller resultant VB, the velocity of the boat with respect to the ground. Since the current is acting against the direction of the rowing boat, the speed of the boat in this case, as observed from the ground, will be slower than the speed in still water. Now these are all cases where the rowing of the boat and the river current are in the same direction, maybe parallel or anti-parallel. So we consider this as a single-dimensional case, and we'll move to two-dimensional cases later in this series. But before that, let's put some numbers to what we have learned in this lesson. We are given that the velocity of the boat with respect to the river is 3 meters to the right. This means that the boatman can steer the boat at 3 meters per second in still water. The velocity of the river current is given as 2 meters per second, and both are in the same direction, that is to the right. So in vector terms, the direction I. We are asked to find the velocity of the boat with respect to the ground. How fast does the person on the ground see the boat moving? We've seen that the velocity of the boat with respect to the ground can be expressed as the velocity of the boat with respect to the river plus the velocity of the river. So VB equals VB with respect to R plus VR. And this turns out to be 5I, which means that a stationary observer on the ground will see the boat moving at 5 meters per second. The boatman is rowing the boat at 3 meters per second, and the river current is aiding the movement of the boat along the same direction at the rate of 2 meters per second. The boat moves faster than it would in still water, since the current is helping the boat by being in the same direction. And in the vector diagram, you can see that the resultant vector is longer than the individual vectors. Now let's see what would happen when the current is in the opposite direction. We use the same formula, that is, VB equals VB with respect to R plus VR. Now VB with respect to R is 3 meters per second, and VR is minus 2 meters per second, and minus since the current is in the opposite direction to the rowing of the boat. And we obtain the velocity of the boat as 1 meter per second, which is slower than the rate at which it is being rowed. So to a person standing on the bank of the river, the boat is moving towards the right at 1 meter per second. And in this vector diagram, you can see the resultant vector is shorter than the vector representing the velocity of the boat with respect to the river. Suppose there was no current, then how would this picture appear? Now we take a case where there is no current, and in this case, VR will be 0, and therefore VB and VB with respect to R will be identical vectors. In such a case, an observer watching from the river bank will see the boat moving at exactly the same velocity as the boatman is rowing the boat. In this lesson, we have looked at cases where the rowing of a boat and the river current may be in the same direction or in exactly the opposite direction. The addition of the river current velocity with the boat with respect to the river velocity is the velocity with which a stationary observer on the river bank would see the boat moving with. It will appear faster when both are in the same direction and slower if the directions are opposite.